are the gaps and how we are going to improve those techniques in the future, and what are the tools that are needed to be used in this process. So please feel free to ask questions or have a brief discussion.
Arben, you have a couple of questions in the Q&A, but I have one quick question I'd like to ask the presenters, if I could. In the spirit of the workshop, we're very interested in end-to-end applications and getting to the point of actually being able to calculate engineering risk in a performance-based earthquake engineering sense. And all of this work is exciting and very interesting of the complexity of the fault rupture. I was just wondering if anybody on the panel or the presenters has a notion of how all this information can most efficiently get distilled down into a form that can enable engineering risk assessments. And at the end of the day, engineers are going to have to evaluate a finite number of rupture scenarios. And one of the big questions is how many scenarios, and do you fully encompassed in some sense the risks? So I would just like to hear the view of some of the presenters on that topic, if they have an opinion or point of view.
Okay, so yes, that's a very important and very good question. Well, let's start with answering two questions for Rob. I don't know, Rob, can you read the question?
Sure. So first question, the slip distribution you characterized are based on low frequency inverted source models. And now the change in the shape of the slip rate function is to produce higher frequencies. The question is, have you tried just changing the acceleration time and keeping the slip rate function the same? That is a heterogeneous acceleration time across the fault. Well, yes, and in a way that's done. So if the shape of the slip rate function is exactly the same as it is in the standard GP method, and you keep the rise time the same, constant rise time across the fault, then that acceleration will go up, or the peak slip rate will go up. It turns out that doesn't do so well. And in fact, to get the accelerations, the higher frequencies, it's more related to the temporal changes, and in particular, the rupture speed. So the rupture stopping and starting, that's what gives you high frequencies. The slip patches, not so much. Now, what I presented was how in the shallow part of the fault, when it's velocity strengthening, that can actually remove some of the higher frequencies. There's a second part of this question about differences between simulated and observed waveforms. Therefore, I think more validation is needed. But sure, more validation and rigorous validation is always needed. The point in this particular presentation was it's not an inversion. We're not trying to match exactly every bump and wiggle, but we more wanted to show that if the GP method is used in a kind of predicted forward sense, can we produce realistic looking waveforms? Arben, do you want me to go to the second one? I don't want to take a whole time here.
Yeah, well, the second one, I think the answer is going to be very short, but
yeah.
Please go ahead.
Let's see. You mentioned you compared the acceleration response vector recorded and simulated for Ridgecrest. Beyond that, did you or any of your team apply the recorded and simulation motions directly to any structure and compare the resulting structural response? Such comparisons might be useful towards acceptance of synthetic motions. Yes, exactly. And there's actually going to be some talks, I think, later. And just off the top of my head, Greg Deerline, Farzin has also used the synthetic responses in looking at engineered structural response. And this is a key concept that is, and I think that also gets back to what David is talking about, is from an engineering perspective, what are the requirements to be able to say, yes, this method is acceptable, or these motions are acceptable, or we need to do 50 realizations or 5,000 realizations. I think it really has to do with looking at those kind of ground truth engineering response metrics. So thank you very much for those questions.
Okay, so Martin or Euro, do you guys want to answer the question that Dave asked to us panelists and also attendees?
And Arben, let me just say, I apologize for asking it verbally, but as panelists, we cannot enter into the Q&A box, so I had to do it verbally. So thanks.
That's fine.
Well, I'm happy to, but I have to admit it was a very long question. It had multiple parts. So if you can break it up in smaller pieces, that might help. You mentioned something about statistics and how many simulations we ought to do, but then you also had something that led up to that final comment.
Yeah, I just think as the engineering community, an application of end-to-end simulations is being faced with the question of how many rupture scenarios do I need to incorporate in order to have a feeling that I've encompassed the full breadth of the hazard and risk for a particular structure. And I'm just curious, these are very complex models with a lot of knobs to turn, if you will. And how can we distill that down into something that's simple enough that we can inform the engineering community? If you look at this variation of the fault rupture parameter space and include, I'll make up a number, 20 rupture scenarios, you probably got a fairly reasonable characterization of risk. And I know that's a sort of a generalized question, but it's one that the engineers are rapidly becoming faced with as we think about application of these methodologies.
Mm-hmm. So I wouldn't settle on a precise number. It depends on a particular location and the prior knowledge you have or the certainty you have on that knowledge. I mean, if your fault system is very well characterized and you have what you consider a reliable 3D velocity model, I think you can get away with much fewer simulations than if that wasn't the case. Now, actually, David, you made a very profound statement in your initial opening slides that it does matter, for instance, where the rupture nucleates. So whether it propagates from south to north or north to south, and that's absolutely key. So in the sense, what I mentioned, when you have a starting heterogeneous distribution of slip and other source parameters, I mean, you have to vary on top of that the nucleation point. And so if you say, I'm considering scenarios of bilateral rupture versus unilateral rupture in various directions, slight modifications in the hypercenter, you quickly get to dozens or even not hundreds of simulations if you want to randomize for each hypercenter location over your, let's say, 20 or so rupture realizations. So, there is an aspect of stochasticity. So it's 20 to 30 simulations to get a stable distribution. But then there's sort of these deterministic features of where the rupture nucleates. At least to me, this is not almost deterministic that we need to consider. So I would say initially, this is what we're looking at. Having said that, and I believe the workshop will go into that, in the near future, we will begin to apply all kinds of machine learning algorithms to these large data sets, large simulation data sets we generate. And maybe something magic pops out there that will allow us to get away with much freer simulations. I don't know yet. I see Rob is nodding his head. Yeah, we'll do machine learning. But earthquakes are so darn complicated. And let's face it, every single new event for which we have a dense recordings teaches us a new lesson. So,
I just want to acknowledge this as a key challenge for the engineering application of some of these more sophisticated characterizations of the rupture model. And it just seems like something that is going to take a very careful look to move it into the domain of being able to apply. So anyway, I appreciate the perspectives, your perspectives on this. Thank you very much.
So I would like to add one thing. Yeah, it's this is a question that we just have started asking, and there's no answer to it. But there is a lot of work that is done, and it's published in literature, regarding rupture dynamics modeling, although those models are not constrained at very high frequencies, but there's a lot of knowledge about how much variability we will expect among those scenarios. And there are databases that are, I'll say 100 and up to 300 rupture scenarios. And probably Martin has some something to do about it. But my understanding is that it's very important to single out those parameters that actually matter the most when we move them around. And we already have found that one of them is the slip distribution, which has to do with variability at a given site. But the second one is the rupture initiation. And although that does not really affect the high frequencies, but it does affect the long period. And then the third one is going to be the rupture velocity. We still have no really good knowledge about how the rupture velocity changes from one type of earthquake to another, or even within one rupture. So those are the three parameters that I think we could rely on rupture dynamics to have some ideas about what will be a good number of realizations. And I think Martin also mentioned about the hypocenter location. That's something that is based on observation. So that's something that can be easily done. Write a small code that will allow you to generate very possible rupture initiation. And then we can start from there. But my understanding is that if we look at the single site, the number of rupture parameters needed to capture the whole variability is not going to be in the order of 100 or 200, because we already know that most of those kinematic rupture parameters are intercorrelated with each other.
Yeah, that's a good point, this correlation. And we need to figure out which one has the strongest predictor capability. So which one should we really focus on and constrain? And then as we go down the correlation chain, that gives us the most bang for the buck, so to speak.
Yeah. I have something I might want to add, but I want to give Haroe a chance. If she, do you have any comments on this?
For the realization number, I don't see the big difference between 50 realization and 100 realization on the Skek Broadband platform. So maybe 50 might be the one of candidate.
Okay. Just to add very quickly, another way to approach this is not just looking at a single site and what the ground motions happen, how they vary at that site, and but do a whole array of locations. You don't necessarily, and then you could have one rupture. Maybe there's super shear in the beginning portion, but sub shear in the latter portion. If you sample along the strike at different locations, you can actually kind of get, as Martin had said, more bang for your buck by just looking at multiple sites in terms of the ground motion response. The other thing, and I think it's really important, is to try to develop kind of generalizations, or look for the systematics of this. And this really requires kind of the collaboration between earth scientists and engineers, where the engineers have all the expertise and the knowledge about the structures and how they respond, but then they can say, oh, well, here, this certain type of motion, this pulse is, causing problems to my structure. What causes that pulse? And the earth scientists can go back and look and say, oh, well, that's happening, when the rupture velocity is, like this, or the slip patch is between the hypocenter and the site, and things like that. And that's where I think we're going to make some progress on this.
Yeah, very good. Good point. Thank you.
There are a couple of comments. Two of them are by Hiroshi Kawase. Is there any way we can give him the microphone, or I should read those? He already typed those in the question and answer. All right, so I'm going to read those, and maybe other people can, answer those. But Hiroshi has this comment. I think that the seismologists should not answer this kind of question because we cannot constrain all parameters needed in the physics-based model, where all the parameters should be constrained by observed data. In other words, engineers should use variability of the observed one, not from the physics-based simulations. Well, I partially agree with that, but I think the reason why we're trying to use synthetic ground motion is that we don't have enough data to actually study the building response at given locations or given magnitudes or given rupture type. So we don't have enough data to really constrain the number of realizations that we should consider, or the number of recorded scenarios that we should consider. So that's why I'm saying I partially agree with that, but
Yes.
we need to start using our synthetics to actually help engineers.
Yes, the synthetics is good to interpolate the observation, but not extrapolate. So the
Yeah,
should follow the observation on the average, so that we can interpolate the near foreground motion by synthetics. I agree, but for the question is the variability of the ground motion, and if we change the parameters one by one, and every parameters we have say 10 or 15 parameters, so that if we change each parameters with the standard deviation, then we end up with 100 times of variability. That's not observed variability. So
Well, but the question we have is that how much of that variability will affect the building response? That's what David is asking. We know that there's every single scenario that has its own response, but we need to check that with the building response itself to see how much that will change the response and the variability at a given site.
So the variability of observed ground motion as a kind of ergodic assumption is the largest variability that we should face with. And the variability coming from the physics-based simulation could be much larger than the observation. And if it is larger, then we should not use that variability in design. That's my point.
yeah. Well, I'm with Arben on this. I partially agree, but Hiroshi, I think that it is important that we are able to extrapolate to conditions that we haven't observed yet. And observed meaning that we don't have enough recordings, say a particular magnitude, large magnitude in close to the fault, where, and also sampling the variability, that, say super shear rupture versus, being next to an asperity and things like that. So we can simulate those. And I agree, it's, you have to have confidence in your simulations. And the kind of the backbone there is that if we have physical models that, and then we're letting the physics kind of dictate how we do the extrapolation. Obviously, they need to be validated, but that would be the key point there, is that there are cases on it from an engineering perspective where extrapolation is needed. We don't have all the observables.
Well, extrapolation is okay, but extension in parameters is not. So we don't know beforehand what is the proper range of slip velocity or proper range of rupture speed. We know average.
Yeah, or maybe we have
specific fault.
Yeah,
it can be either 60% of the shell velocity or 85% of the shell velocity or super shear. We don't know beforehand.
Yeah, that's a good point. And what we can do though, is actually carry that all the way through to the engineering analysis. And maybe it doesn't matter so much if it's, 60% or 70%. Maybe it only matters if it's, 75 to 90% or something like that. I'm just, hypothetically. And that's where this kind of feedback between the engineers and the earth scientists can be very helpful. Again, from an engineering standpoint, maybe some parameters or a range don't really have an impact on the engineered structures. And that's, I think, where the stage we're at is trying to explore if there's some guidance or constraints that can be obtained from doing those types of analyses. So you're absolutely right, Hiroshi. I agree with you. We don't know what those ranges really are.
So please don't misunderstand what I'm saying. I'm not saying that physics-based simulation is useless. I'm saying it is useful, but in terms of the variability, it is very difficult to determine solely from the physics-based simulation.
Okay, Kawasan, I would like to add another optimistic comment that was just written right now, and then I'll go to a question, general question. So the optimistic view is from Idris. He says that there have been huge advancements in this field over the past 50 years or so. So keep up the good work, and let's keep on adding tools to our toolbox, and let us continue to use the results with prudence. Yeah, prudence it's what Kawase-san is talking about, and I think this is a really good comment, and it makes us feel a little bit better. But there is another question which is more specific to the quality of the synthetic data, which is written by Arsam Taslimi. He's asking whether the synthetic data can reproduce or predict the vertical motion. The vertical and rotational component of the ground motion as well. I think this is a very good question, and we're just touching to it. But the beauty of the simulations, at least the deterministic ones, is that we could actually produce ground motion on a very dense grid and check the correlation between adjacent points and also the rotation. But that's something that it's worth looking at. And I think our techniques might be helpful to answer some of the questions that we have based on recorded data. There's another comment from Swaminath Krishnan. It says, in the absence of data from large earthquakes in urban areas, we have no choice but to use the simulations to be prepared. We can certainly incorporate the uncertainties, but we cannot ignore what has already been done. And I certainly agree with that. And this is the purpose of this forum, that I think we need to be open to each other and express the concerns, as we're already starting right now, and probably we'll find a dialogue and get more engineers involved in testing our techniques and validating our synthetic ground motion. As seismologists, we tend to apply a little bit more ideas that are related to seismology, and we forget about what's matter about the building itself. And this conversation, this dialogue is extremely helpful, and I think we ought to continue in the future.
Yeah, I just want to comment actually. So Swami's question actually reminded me that one of the kind of early studies that Swami was involved in had to do with looking at the response throughout the Los Angeles region for a large San Andreas rupture, and how that might impact a particular type of building or a couple different types of buildings, kind of, example structures. And what they did is they didn't just put that building, say, in downtown Los Angeles to see what had happened, but they moved it effectively all throughout, locations in the Los Angeles region. And the idea there was they weren't trying to match a specific building in a specific location, but they could take advantage of that dense distribution of ground motions to see what the characteristics were and how they impacted the building. So even though they were really only looking at one scenario event on the San Andreas, they got a lot of use out of the variability in ground motions.
All right, thank you, Rob. We're running out of time, but we will come back to this discussions tomorrow.